For this experiment, you know you've got 6 samples, 1 plane, and then you've got various stress razors through the other samples. You've seen the CAD, you've done the modelling, you've got a good idea about what's going to happen. Assignment itself, the 3 main sections are a description of the experiment, then answer some set questions on the experiment itself and present the data. You've got some force displacement curves and stress strain. You have to work out engineering stress and true stress strain curves.
We've got 6 different types of tensile bars. First of all, we've got the plain one. I'm going to start by putting this on. Machine. Yeah, of course. So it measures the amount of displacement, the amount of extension, which you can convert into strain. And it also measures the amount of force that's required in order to create that level of extension.
While taking part in the experiment, lab coats, safety glasses and gloves should be worn.
This will be output into an Excel file. What you then do is convert the force and the displacement into engineering stress versus engineering strain. This is the force versus displacement curve. So you've got force in newtons on the y-axis and then displacement in microns on the x-axis. This is how the data comes out from the machine. You've got basically the time in seconds, displacement in microns, force in newtons. This is the straight part, basically the straight part of the curve. That's the elastic region, and then after that's the yield point. That the ultimate tensile strength will be up in that region there.
The key thing about the entire assignment is that you've got 3 different routes by which you can evaluate the effect of the stress ratio on the strength of the component. You've got the empirical method, where you've got a series of equations that give you stress concentration factors, and you've got your experiment, which will give you force displacement, and then you can also work out stress concentration factors from Newton's rule, and then you've got the modelling, which will, at its most simple, give you out a graph or data of force displacement, much the same way as you will come out of the machine. In all of these cases, you can work out stress concentration factors from the 3 different routes. So the ultimate aim here is to be able to say, right, this is the empirical, this is what our experiment told us, and this is how the modelling told us stress concentration factors. Some are out, why are out, what's out. Okay. The thing to note is that these plane samples, when you do these are the way you actually get material properties in the first place. So these plane samples give you all the data you need, the elasticity regime, it gives you the yield strength, and the ultimate tensile strength. Okay. And they're all in that one curve. So, and that was the one curve that we used in the model, a multilinear flow rule, that has everything in it. So you don't have to go off looking for Young's modulus or density or anything for this material. You don't actually know it, because you don't know exactly what material it is, but that curve gives you everything you need. And that curve is the one that's being used by the model. So, you can use your own data from either one of these 2 plane samples and change that so it fits your models of the experiment better than I did. Because what I did is I based it on data from last year, and the samples were prepared in a slightly different route. Okay, it was CNC machine last year, this year they've been plasma cut, and there could be a bit of difference between them. So you have the best data for your own particular group. This material is representative of all the others. One thing to do, if you are going to do that, and that really is the very, icing on the cake to do all of that on this assignment. I know you don't have a lot of time, but at least you don't have to develop models. It's not that difficult. You can put a curve to this with 14 points, and you just replace the data that's already in there with the one that's from here, and see if you get any closer. One point to note is that the gauge length is important to be able to determine the elongation. And the one place where I expect, even if you don't get that strain, because you have a true stress, true strain curve there, the strain is dependent upon the definition of your elongation, of your initial gauge length. So I used 70 millimeters, but mine is slightly out. So I'm getting a 20 millimeter displacement at the ultimate tensile breaking point. Whereas actually you get about 30 millimeters. So I did something slightly different. Whether you guys can correct that or not, that's the icing on the cake. You'll run the rest of the models. You've run 2 so far, one on the plane and one on the 2mm hole, and you can run the rest of the models as well, extract the data. You would expect a couple of references for this, particularly for the empirical holes. Don't just reference Blackboard and my notes. Try to find out who has actually got a book that has got that table and data in there. I think it's Pikey 2007 or something like that. I've given you the equations for the stress concentration factors for the holes in the middle and the double notch. I haven't given you the one for the single notch on the side, but it is out there. There's an equation for that as well. Okay?